Hello viewers, welcome to the 8th lecture of this course on mathematical finance, which is going to be the second lecture of module 3. So, in this lecture, we are going to look at some of the results for the two asset portfolio. So, remember in the previous class, what we had done is we had defined what is the return of an asset for a single time period, and then we looked at a portfolio which comprised of two assets which are both risky, and we looked at what is going to be the return of the portfolio, and we had done one result, that is the return of the portfolio is going to be equal to the weighted sum of the returns of the two individual assets, and then we used it to define what is going to be the expected return of the portfolio of two assets. Now, recall that in the Markowitz framework, the two main pillars were return and risk. So, we begin today's class with a theorem on the risk that is associated with a two asset portfolio. So, we state the theorem as follows. So, the variance var kV for a portfolio of two securities or assets is given by var kV is W1 square, remember this was the weight of the first asset, into the var or the variance of K1 plus W2 square into variance of K2 plus twice W1 W2 into covariance of K1 K2. So, we will do the proof for this. So, for the proof we begin by recalling the expression for the return of this two asset portfolio. So, recall the expression of kV is equal to W1 K1 plus W2 K2. Therefore, variance of kV is going to be by definition expected value of kV square minus expected value of kV whole square. This is going to be by definition. So, I square this term of kV. So, this gives me W1 square K1 square plus W2 square K2 square plus twice W1 W2 into K1 K2. And for the second case, you remember that we had this result that E of kV or the expected return on the portfolio is going to be W1 into the expected return of the first asset plus W2 into expected return of the second asset. So, we substitute the E of kV here, that is W1 E of K1 plus W2 into E of K2 whole square. So, opening this up, what do we get? We will get, so we make use of the linearity property now. So, this term E of this W1 square K1 square, this can be written using linearity of expectation as W1 square into E of K1 square plus W2 square into E of K2 square plus twice W1 W2 into E of K1 K2 minus we will get the second expression, which will be W1 square into E of K1 square plus W2 square E of K2 square, we are just using the A plus B whole square formula, plus twice W1 W2 into E of K1 multiplied by E of K2. So, continuing with this, so what we will do is that we will combine terms. So, let us combine the W1 square term first. So, we will get W1 square multiplied by E of K1 square minus E K1 whole square. Then we will consider the W2 square term. So, accordingly we get W2 square E of K2 square minus E of K2 whole square, and then we will take into account the cross terms W1 W2. So, we will get twice W1 W2 E of K1 K2 minus E K1 into E of K2. So, observe carefully, this particular term here is E of K1 square minus E K1 whole square. Remember that K1 is a random variable. So, by definition of variance, this term that we have here, this term can be replaced with variance of K1. Likewise, this term that you have here, this is going to be variance of K2 plus twice W1 W2, you have this term. So, remember we had covariance of xy was E of xy minus Ex into Ey. So, this term will become covariance of K1 K2. So, now we essentially what we have now is that given the following input, that you know what is the return for the first and the second asset, and consequently you know the expected return for the first and the second asset, and also you know what is the variance or standard deviation which you take as the risk of the returns of both the assets, and you also know the information about the covariances of both of them. So, using these three pieces of information, we can then construct the return or the expected return for the portfolio as a whole and the risk of the portfolio as a whole. So, for a wide variety of choices or a wide range of choices of W1 and W2, we can examine case by case as to what is going to be our expected return and risk, and then accordingly make our investment decision. So, for the sake of brevity and convenience, we just briefly introduce a simplified notation for some of the input parameters that we are going to use in the course of our discussion on this two asset portfolio. So, we now introduce the notation mu v. So, we will denote mu for the expected return. So, accordingly we will define mu v or identify mu v with expected return of k v. Mu 1 will be given as E of k 1 and E of k 2 will be denoted as mu 2. Likewise, the risk, which is the standard deviation of k v in case of the portfolio, this will be denoted by sigma v, and sigma 1 will be square root of variance of k 1, and finally sigma 2 is square root of variance of k 2. Okay, and there is one final notation. So, we essentially have defined this term. So, finally, one more term is left, that is covariance of k 1 k 2, and we will denote this by a lowercase c 1 2. So, it is a covariance between the first and the second assets return. Hence, the two results that we have obtained for the expected return and the risk for this two asset portfolio can now be written in the simplified notation that we have just introduced as mu v is equal to W 1 mu 1 plus W 2 mu 2, and sigma v square will be W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 C 1 2. Now, this particular term can be rewritten in another form, giving us the following expression: W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 into sigma 1 sigma 2 multiplied by rho 1 2, where rho 1 2 is C 1 2 over sigma 1 sigma 2. Remember that this is nothing but the correlation coefficients, which is the covariance between the two random variables divided by the standard deviation of the first random variable multiplied by the standard deviation of the second random variable. So, here this is the correlation coefficient, provided the denominator is not 0. So, that means provided both sigma 1 and sigma 2, these are not equal to 0. So, in case of sigma 1 sigma 2 is equal to 0, then rho becomes undefined. However, from a financial point of view, if you have either sigma 1 equal to 0 or sigma 2 equal to 0 or both of them 0, in each of those cases it implies that the asset is no longer risky because of 0 risk measure, which in this case is standard deviation, and hence the portfolio no longer remains a portfolio of two risky assets, but instead it becomes a risk free asset. So, that means that if your sigma 1 equal to 0 or sigma 2 equal to 0, this essentially becomes that the security is risk free. All right. So, now let us look at a motivating example. So, let us consider three scenarios as before, but not necessarily recession, stagnation and boom that we have defined previously. So, just we identify three different economic scenarios, omega 1, omega 2 and omega 3, and the corresponding probability of each of those scenarios are 0.2, 0.4 and 0.4 respectively. So, we consider two assets with returns k 1 and k 2. Now, the return k 1 in the first scenario is minus 10% or minus 0.1. In the second case, it is 0%, 0, and the third case is 20% or 0.2. Identically, in case of the second asset, the returns are 5% or 0.05, 30% or 0.30 and minus 5% or minus 0.05. So, now what we want to do is that we want to construct a portfolio, in particular a two asset portfolio out of these two given assets with the specified returns under three different scenarios. So, accordingly what we do is that suppose we start with a portfolio, and remember, for a portfolio we must specify what the weights are. So, we start with a portfolio with weights W 1 equal to 0.4, that means 40% of the wealth is allocated to the first asset, and W 2 naturally in that case is going to be 0.6 or 60% being allocated to the second asset. Then you can compute the variance of returns of the first asset using the basic definition of variance, and this is approximately 0.0144, and for the second asset this is 0.0254, and the correlation between them rho 1 2 is minus 0.6065. So, they essentially they are negatively correlated. That sort of should be obvious, considering the fact that in the first scenario omega 1, when the first asset is incurring losses or negative returns, you get a positive return in case of the second asset. In the second scenario, when the return is 0 for the first asset, you get an extremely high return for the second asset, and the third scenario, when you have a return that is fairly high in case of first asset, you observe that the return in case of the second asset becomes a negative quantity, that means it is incurring losses. So, at a first glance, when you compare these two returns and finally these two returns under omega 3, you observe that the pattern of returns is behaving in a somewhat opposite direction, which is suggestive that your correlation coefficient is likely to be negative, which it actually turns out to be minus 0.6065. So, therefore, we can use the formula sigma for sigma v square to obtain W 1 square, which is 0.4 square, multiplied by sigma 1 square, which is 0.144, plus W 2 square, which is 0.6 square, multiplied by 0.0254 square, plus 2 into W 1 0.4 into W 2, which is 0.6, into rho 1 2, which is minus 0.6065, multiplied by sigma 1, which is square root of 0.0144, multiplied by square root of 0.0254. So, this should actually be there should not be any square. So, this is your W 1 square, this is W 2 square, this is twice W 1 W 2, this is sigma 1 square, this is sigma 2 square, and this is sigma 1 sigma 2, and this is rho 1 2. So, this turns out to be equal to approximately 0.00588, and you observe that this sigma v square, which is 0.00588, is less than sigma 1 square and also less than sigma 2 square. So, what this suggests is that you have a portfolio variance is less than variance of each of the two assets, and this example illustrates the benefit of actually making an investment in a portfolio rather than just investing in one particular asset. So, this example motivates the following theorem: the variance sigma v square of a two asset portfolio cannot be more than the maximum of the individual variances sigma 1 square and sigma 2 square. That is, sigma v square, which is the variance of the portfolio must be less than or equal to the larger of sigma 1 square and sigma 2 square, provided no short sales are allowed. So, let us look at a proof of this. So, for the proof we can consider two cases. Suppose sigma 1 square is less than or equal to sigma 2 square. Now, given the condition that there is no short selling, remember that a short selling is a scenario where we borrow the stock from our owner and sell it off in the market under the assumption that the stock price will go down, and that subsequently we can purchase it for a price that is lower than the one that we received by selling of the stock and return it to the owner of the stock. And this act of selling without having the ownership is known as short selling, and so this weight in this case is denoted by a negative number. So, accordingly, given the condition that there is no short selling, so obviously the weights cannot be negative, and so we have W 1 greater than or equal to 0 and W 2 is greater than or equal to 0. So, therefore, W 1 sigma 1 plus W 2 sigma 2 will be less than or equal to W 1 sigma 2 plus W 2 sigma 2. Why have I made this statement? Here I have made use of the fact that sigma 1 square is less than or equal to sigma 2 square. So, I have made a change to this particular term. Now, this can be written as W 1 plus W 2 into sigma 2, and remember that W 1 plus W 2 is equal to 1. Further, we recall that the correlation coefficient from basic probability, we get correlation coefficient lies between 1 and minus 1. So, therefore, sigma v square is equal to W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 sigma 1 sigma 2 rho 1 2. This is going to be less than or equal to W 1 square sigma 1 square plus W 2 square sigma 2 square plus W 1 W 2 sigma 1 sigma 2, since rho 1 2 is less than or equal to 1. Now, this term or this expression now has become a perfect square. So, I can write this as W 1 sigma 1 plus W 2 sigma 2 whole square. And here you remember W 1 sigma 1 plus W 2 sigma 2 is less than or equal to sigma 2. Therefore, I can write that this is less than or equal to sigma 2 square. Remember that I had assumed that sigma 1 square is less than or equal to sigma 2 square. So, therefore, sigma 2 square is nothing but the maximum of sigma 1 square and sigma 2 square. So, for the case 2, if we assume that, suppose that sigma 2 square is less than or equal to sigma 1 square. Remember, in the first case we chose sigma 1 square less than or equal to sigma 2 square. So, in this case we will make this particular assumption and the proof is analogous or similar. Now, going back to the statement of the theorem, we have said that this result holds provided no short sales are allowed. So, naturally, I am curious about as to what will happen if there is actual short selling. So, the question is that what happens if there is short selling. So, again we considered the previous example, but the only thing that changes now is instead of W1 being equal to 0.4, we change this to minus 0.5, that means we are short selling the first asset, and W2 being equal to 0.6, we change this to 1.50, right. So, the W1 plus W2 adds up to 1. So, in this case your sigma v square will be approximately minus 0.5 square, which is W1 square, into sigma 1 square, which is 0.0144, plus W2 square, which is 1.5 square, into sigma 2 square, which is 0.0254, plus twice W1, which is minus 0.5, into W2 1.5, multiplied by square root of sigma 1, this is 0.0144 into 0.0254, multiplied by rho, which is minus 0.6065. And now you see, in this case this sigma v square turns out to be 0.2795. And interestingly, in this case sigma v square is greater than sigma 1 square, which is this, and sigma v square is greater than this, which is sigma 2 square. So, in this case, as a result of short selling, what has happened is that the overall risk of the portfolio has increased and has reached a point where it is actually larger than the risks that are there for each of those assets individually. So, we next come to something which is known as the feasible set. So, as the term feasible suggests, this means what is the possible set, and that is what we are going to address. So, what is a feasible set? And the answer is the collection of all portfolios that can be constructed by investing in two given assets is called the feasible or attainable set. So, each portfolio can be represented by a point with coordinates sigma v mu v in the sigma mu plane. So, we will explain this in more details graphically. So, this immediately brings us to another question, is what is going to be the shape of the feasible set in the sigma mu plane. So, to address this, this set or the feasible set comprises of points with coordinates sigma v square, coordinates sigma v mu v, where your mu v is w 1 mu 1 plus w 2 mu 2 and sigma v square is equal to w 1 square sigma 1 square plus w 2 square sigma 2 square plus twice w 1 w 2 multiplied by C 1 2, where w 1 w 2 belongs to R or are just real numbers, assuming that short cells are allowed, and w 1 plus w 2 is going to be equal to 1. So, what this really means is the following, that I choose say one w 1 w 2 and this will give me one set of mu v and sigma v making use of this particular formula. Then I will have another set say w 1 tilde w 2 tilde of weights and this will give me some mu v tilde sigma v tilde. I might have another third pair of weights w 1 bar and w 2 bar and this will give me the expected return mu v bar and sigma v bar as the risk. So, the feasible set essentially is the collection of all such portfolios which will result in these points being plotted on the mu sigma diagram with the sigma on the x axis and mu on the y axis. So, since now, when you are talking about the question about what is the best choice, right, I mean effectively when I have said that w 1 and w 2 can be real valued. So, for all practical purposes you are essentially getting an infinitely many different possible such portfolios and you want to figure out what is going to be the best choice of the portfolio, particularly from the context of minimization of risk, and motivated by this we now parameterize mu v and sigma v by writing as follows, that since w 1 plus w 2 is equal to 1, we choose w 1 equal to s and w 2 is equal to 1 minus s. So, remember in this expression for mu v, your mu 1 and mu 2 are known. Likewise, or estimated making use of the historical data for each of the assets, and sigma 1 square, sigma 2 square and C 1 2 are the known terms in case of sigma v square. So, accordingly, the only two terms that actually can vary are w 1 and w 2. Now, taking advantage of the fact that w 1 plus w 2 is equal to 1, we rewrite w 1 to be equal to s, which obviously gives w 2 to be equal to 1 minus s. So, what this does is that this will result in parametrization of the feasible set by one parameter, and accordingly I can rewrite mu v as s into mu 1 by writing this as s, and I write this as 1 minus s plus 1 minus s into mu 2, and I get my sigma v square to be equal to, so I replace this by s, 1 minus s, s, 1 minus s. So, I replace this with s square sigma 1 square plus 1 minus s square sigma 2 square plus twice s into 1 minus s into C 1 2 with s in R. So, now what you have is that you have the advantage that earlier where mu v was parameterized in terms of two variables W1 and W2, and you have now rewritten the same thing in terms of one parameter, namely this S. So, now what is the reason for me switching to a single parameter form of writing the expected return and risk of the portfolio? So, let me address this by posing a question, and the question is that among all feasible portfolios, how does one determine the portfolio with the smallest variance, and smallest variance obviously means the smallest standard deviation. So, I can write or equivalently the smallest risk. Okay. So, what you do here is that we are considering this two asset portfolio, and what you can do is that we can sort of laboriously work on trying out various combinations of W1 and W2 and calculate the mu v and sigma v square and check on a case by case basis which will be the lowest sigma v square. However, given the freedom that W1 and W2 are real valued, this from practical point of view is impossible for us to make a decision on the pair of W1 W2 that is going to give you the smallest sigma v square. So, that is the reason why we chose W1 to be equal to S and W2 equal to 1 minus S, so that the variance sigma v square, which was previously dependent on two variables, namely W1 and W2, now gets reduced to something that is dependent on one variable, or in practice sigma v square has become a function of a single variable. So, if I am trying to maximize or minimize sigma v square, then all I am trying to do is minimize a function of a single variable, namely small s in this case. So, it is this amenability or the convenience of using basic differential calculus to ascertain the value of weights W1 and W2 that will give us the minimum risk portfolio. That is why we have chosen W1 to be equal to S, and automatically I will get my W2 is equal to 1 minus S after I determined the S which minimizes sigma v square. So, we can put this now as a theorem. If rho 1 2 is strictly less than 1, and when it is equal to 1 we will consider the case separately, or if sigma 1 not equal to sigma 2, then sigma v square as a function of the parameter S will attain its minimum at S equal to S0 sigma 2 square minus C12 over sigma 1 square plus sigma 2 square minus twice C12. Further, the corresponding values, and by corresponding I means the one that is corresponding to this particular S0 which minimizes sigma v square. So, the corresponding values of mu v and sigma v square are given by mu v, and we could call this particular mu v as mu naught, as mu 1 sigma 2 square plus mu 2 sigma 1 square minus mu 1 plus mu 2 C12 divided by sigma 1 square plus sigma 2 square minus twice C1 2, and likewise sigma v square is equal to sigma naught square is given by sigma 1 square sigma 2 square minus C1 2 divided by the same denominator sigma 1 square plus sigma 2 square minus twice C1 2. Now, we started off by saying that if rho 1 2 is less than 1 and this condition holds. So, if this condition does not hold, which means either this is true or this is true. So, that means the left out condition is that when rho 1 2 or the correlation coefficient is 1 and both the variances of the assets are identical, then all feasible portfolios will have the same variance namely sigma 1 square is equal to sigma 2 square. Okay, so let us look at a proof of this. So, let me split up the proof into two cases. So, I will consider this to be the first case and this to be the second case. So, case 1, when rho 1 2 is not equal to 1 or sigma 1 not equal to sigma 2. So, observe that sigma v square, which is synonymous with the risk because that is just the square of the risk which is given by the standard deviation. So, you first observe that sigma v square, which is the function of a single variable x, will attain its minimum when the derivative of sigma v square with respect to s is set to be equal to 0. So, basically sigma v square, which is now a function of a single variable, the minimization of that will be done by making use of the derivative test that you have seen in differential calculus, where the derivative must be equal to 0 at the point where the minimum is attained. So, accordingly, what we do is that we start off with taking the derivative of sigma v square, which now is a function of s. So, I take the derivative with respect to s. So, this is d d s of s square sigma 1 square plus 1 minus s square sigma 2 square plus twice s into 1 minus s into C1 2. So, I have just used the definition of sigma v square in terms of the parameter s. So, the derivative of this turns out to be twice s into sigma 1 square plus sigma 2 square minus twice C1 2 minus 2 into sigma 2 square minus C1 2, and in order to find the value of s at which sigma v square is minimized, we set this derivative equal to 0. So, then solving, we get s equal to s naught. It will be this term divided by this term, which is sigma 2 square minus C1 2 divided by sigma 1 square plus sigma 2 square minus twice C1 2, provided the denominator, this denominator is not equal to 0. So, provided sigma 1 square plus sigma 2 square minus twice C1 2 is not equal to 0. So, I just do a quick check. One, if rho 1 2 is strictly less than 1, which was one of the conditions of for this particular case. So, then sigma 1 square plus sigma 2 square. So, which is the, so let us just examine what is going to be the denominator, or what is going to happen to the denominator under the situation when rho 1 2 is strictly less than 1, and under the situation when sigma 1 is not equal to sigma 2. So, first of all, accordingly I start off with rho 1 2 strictly less than 1. Then the denominator, which is sigma 1 square plus sigma 2 square minus 2i c 1 2. What is this going to be? This is sigma 1 square plus sigma 2 square minus 2i's rho 1 2 sigma 1 sigma 2. And this is going to be strictly greater than sigma 1 square plus sigma 2 square minus 2i sigma 1 sigma 2. Why am I claiming this? Because my rho 1 2 is less than 1, which implies that minus rho 1 2 is strictly greater than minus 1. So, I multiply both sides by sigma 1 sigma 2 to make this conclusion. And what is this expression? This expression is sigma 1 minus sigma 2 whole square, which is greater than or equal to 0, because I have assumed only that rho 1 2 is less than 1. So, that means the denominator under this assumption is going to be strictly greater than 0. So, obviously, this condition is going to be satisfied. And B, if the other condition, that sigma 1 not equal to sigma 2 holds, then sigma 1 square plus sigma 2 square minus 2i c 1 2, this is going to be greater than or equal to sigma 1 square plus sigma 2 square minus 2i sigma 1 sigma 2. So, here I have just used the fact that rho 1 2 is less than or equal to 1. Strictly less than 1 is not required, and that is the reason why I have the greater than or equal to sign here, and this is equal to sigma 1 minus sigma 2 square, and because sigma 1 is not equal to sigma 2, this is going to be strictly greater than 0, which again satisfies this condition. So, under both the premises of the theorem, we are able to prove that yes, indeed this condition is satisfied. So, that means S naught will always exist. Remember that S naught here, the S naught that we have here has the term sigma 1 square, sigma 2 square and C 1 2, and all of them are known quantities. All right. Now, when I am doing the minimization, it is not enough for me to just take the derivative and set it equal to 0. We need to do the second derivative steps also. Therefore, for the second derivative, that is d square ds square of sigma v square. So, we go back to this expression. So, the second derivative is going to be just this term here. So, accordingly we get the second derivative to be 2 into sigma 1 square plus sigma 2 square minus 2i c 1 2, which is nothing but the denominator. And we have already shown for both the case A and case B that this is always going to be strictly greater than 0, and hence minimum is attained at S equal to S naught that we have derived above. Okay. Now, in this case, so if you go back to the statement of the theorem, I said that these are going to be the corresponding values for mu v and sigma v. So, you can obtain these values. So, these are nothing but specific values of mu v and sigma v when you replace S equal to S naught. So, what you need to do here is that in order to obtain, so to obtain mu 0 and sigma 0 or sigma naught square, all you have to do is mu naught is equal to S naught mu 1 plus 1 minus S naught mu 2. So, you just put the value of S naught in both the places and you will get the expression of mu naught that is given in the statement of the theorem. Likewise, you will get sigma naught square will be S naught square sigma 1 square plus 1 minus S naught square sigma 2 square plus twice S naught into 1 minus S naught into C 1 2. So, you replace these values of S naught in these 3 places or 4 places here and do the simplification, and then you will be able to get back the expression of sigma naught square that is given in the statement of the theorem. Alright, now remember that this was the first case when I assumed that rho 1 2 is not equal to 1 and sigma 1 or sigma 1 is not equal to sigma 2. So, I look at the second case now when rho 1 2 or the correlation coefficient is 1 and sigma 1 is equal to sigma 2, both these conditions hold. So, what happens in this case? In this case, sigma v square, which is given by s square sigma 1 square plus 1 minus s square sigma 2 square plus twice s into 1 minus s sigma 1 sigma 2 into rho 1 2, and remember that in this case rho 1 2 is equal to 1. So, this entire expression becomes s sigma 1 plus 1 minus s sigma 2 whole square. Now, observe carefully that here we have sigma 1 equal to sigma 2. So, that means if I replace sigma 1 equal to sigma 2 or if I replace sigma 2 equal to sigma 1, then the s and 1 minus s terms will cancel out. So, you end up getting this to be equal to sigma 1 square or sigma 2 square. So, this is sort of a very interesting observation that basically irrespective of what the weights are, you end up getting the same portfolio risk or variance which is equal to the variances of either of the individual assets. So, it does not matter in what proportion you invest in each of the assets. You may even invest all your money in the first asset or the second assets, or you can take a combination of both. In all cases, the variance is going to be exactly identical, which again makes sense because you understand that sigma 1 equal to sigma 2 means in terms of risk there is very little, or in fact there is nothing to choose between the two, and rho 1 2 equal to 1 means that they are expected to behave in exactly the identical way in terms of the patterns of return. So, that means that from the financial point of view there is nothing to distinguish between both of them. So, effectively they are synonymous with each other, and that means that it does not matter in what proportion you invest in either of them, or if you invest completely in either of them, you end up facing the same amount of risk. All right. So, now coming back to the feasible set. So, the curve described by parametric equations for mu v and sigma v in terms of S for the feasible set in the sigma mu plane is a hyperbola, and we will see how this is a hyperbola. We will state this as a theorem. So, let the correlation coefficient lie strictly between -1 and 1, and let the returns for the two assets be non-identical. Then each portfolio in the feasible set, and by this I mean sigma v and mu v. So, that means that corresponding to each value of W 1, W 2 or equivalently S and 1 minus S, you will get a corresponding mu v and sigma v. I will call this sigma v as x and mu v to be equal to y. So, every portfolio sigma v mu v or equivalently x y, this will satisfy the equation of the hyperbola given by x square minus a square into y minus mu naught. Remember that mu naught was the return corresponding to S naught at which sigma naught square becomes, or rather sigma v square is minimized and is equal to sigma naught square. So, this is equal to sigma naught square. Now, here we already know what is mu naught and sigma naught. These are the mu v and sigma v respectively when S is equal to S naught, that we have already obtained. And one additional term that is not introduced that I have included here. So, I will specify that now, where A is equal to sigma 1 square plus sigma 2 square minus twice C 1 2 divided by mu 1 minus mu 2 square, and this is greater than 0. So, I needed the condition that mu 1 not equal to mu 2 because of the denominator here, and I needed this condition for this numerator here, so that I end up getting A to be a positive number, so that I can look at this as a hyperbola. So, the proof of this is fairly simple, but a little tedious. So, recall mu v is equal to S mu 1 plus 1 minus S mu 2. So, this implies that S is equal to mu v minus mu 2 over mu 1 minus mu 2, and then I substitute S in sigma v square is equal to S square sigma 1 square plus 1 minus S square sigma 2 square plus twice S into 1 minus S into C 1 2, and this will give you your expression. Let me call this expression star. So, this will give your expression star. So, this means that the expression star can be obtained by eliminating S from the parametric equations or expressions for mu v and sigma v square. Eliminate S and you will end up getting the relation connecting mu v and sigma v. Okay, now, so as I have already pointed out before that since rho lies strictly between minus 1 and 1 and mu 1 not equal to mu 2, therefore, A square is greater than 0. Actually, this is A square. A square is greater than 0 and sigma naught square is strictly greater than 0. So, now graphically this looks like as follows. See, on the x axis and this is the y axis. So, on the x axis we have sigma, right. Remember, this is sigma v, and on the y axis we have mu. Then the shape of the hyperbola will look something like this, and these are the asymptotes of this hyperbola. So, this hyperbola basically is the is graphically represented here, and the hyperbola I mean the one that I had indicated as star, and here this is the point where there is a minimum risk, and so therefore, the corresponding risk is going to be sigma naught and the corresponding return is going to be mu naught. So, this particular point here is the portfolio for which S is equal to S naught, and therefore, the corresponding return is mu naught and the corresponding risk is sigma naught. So, therefore, now here this region, now I identify 2 points on this hyperbola, one of them is sigma 2 mu 2. This means that you have invested completely in the second asset, and likewise there is the point sigma 1 mu 1. So, then this particular region on the hyperbola, this is the region which has the portfolios with no short selling. And we have two asymptotes here, this one and this one. The asymptotes are y is equal to mu naught plus minus x over a. So, we have concluded the first part of our discussion on minimization of the risk for a 2 asset portfolio and constructing a feasible set and giving a graphical representation. So, we will continue this discussion and do a little more analysis on this 2 asset portfolio before moving on to the multi asset portfolio. Thank you for watching.